Okay, so this is a very important demo to understand the difference between strength and stiffness. In classical mechanical engineering, you are very concerned about strength. For example, if you build a bridge, you're mainly worried about the strength. If a steel cable, you're worried about the strength, an airplane, and so on. But in instruments and in machine tools, you are mainly worried about stiffness. If you look at a microscope, the frame of the microscope probably could support 1 ton, while in actual use it only supports a glass slide. But it has to be made so heavy, so when you touch the microscope, it's completely stiff, it doesn't flex. Another example, if you look at the bed of a lathe, the bed of a lathe is maybe this thick cast iron, could support easily 10 tons, but the workpiece in the lathe is only 10 kilo. So it's over-designed 1000x because the stiffness is what determines the dimension, not the strength. Or another good example is something like this. This thing doesn't have to take any force because you just put it here to see if things are square, but still it has to be made very, very stiff so it doesn't deflect as you do the measurement. So in many, many industries, you are concerned with stiffness and not with strength, and there is a huge difference. And the best way to understand the difference is if I compare the stiffness of a solid aluminum bar or any metal bar to the same bar cut in two and held with rubber bands. Okay? So obviously the strength of this is no more than the strength of a rubber band. But the question is, what about stiffness? If I put an equal load on both, how will the deflections compare? So to do the test more or less properly, I rounded one end so it doesn't rock. Otherwise, because this is not a precision bar, I have to rest it on 3 points so it doesn't rock. So I rest it here, and I take out any play by preloading it, set the gauge to 0, and load it with a block of steel, and I measure 12 micron. If you look at the gauge, it reaches deflection of 12 micron. Now, I remove the solid bar, replace it with a cut bar with a rubber band. Again, one side is rounded, so it doesn't rock. Put it down here. I have to shim it because of the offset. Make sure it's not sitting on a rubber band. Preload it, same as before. Null it again, okay, to 0. And load it again, and the deflection is now 7 micron. So something very surprising, the bar which is held by a rubber band from 2 pieces is actually much stiffer than the solid bar. Now the reason it's not just equally stiff, but stiffer, is as long as these 2 pieces don't separate, this section behaves like a solid piece. And because that solid piece is twice as thick as the original bar, that section in the middle is much stiffer. It's 8 times stiffer, theoretically, because it's double the thickness. So although this has no strength at all, it is twice as stiff than a solid bar, almost twice as stiff than a solid bar. Okay, so another subject which comes up in design is how to mount pulleys and bearings and things like that. So a couple of simple things to keep in mind. If you look at timing belt pulleys or other pulleys, a lot of them come with a set screw. Now if you tighten the set screw hard here the way you should, you'll not be able to take it off later even if you loosen it. And the reason is because the set screw will make a little dent in the metal, and that dent will interfere with sliding it off. So the first thing you have to do if you want to use set screws, you have to file flats. Okay, if it has to have a higher torque, you have to cross drill with a pin. Okay, but set screws for most small things are enough as long as you file flats. That's the first thing. Now, a better type of clamping, especially if you have a water jet, is some kind of flexure-based clamping where you have a housing which flexes and grips. So this is an example of this kind of flexure-based clamping where you have a split piece with a screw. You put it on here, and when you tighten the screw, the split piece squeezes around the shaft. this doesn't mar the shaft and distributes the load all around it. So it's a much better clamping system, and if you're going to machine the pulley anyway, you can machine in with a water jet some cuts. You can also use the taper plug idea we have seen before for one side to do it. Okay, the other subject which comes up is how to mount a shaft on bearings. So the first thing, two things to keep in mind, that a bearing, a single bearing by itself has a lot of play, and they are designed to have play. So this bearing is a perfect fit on the shaft, but if I put it up here and hold it, you can see how much play there is in the shaft. Okay, the play is not between the shaft and the bearing, the play is in the bearing itself. So there's about this much play in every bearing, even the most precise bearing. Because these bearings were designed always to work in preloaded pairs. So if I wanted to make this shaft in a housing, I would put a bearing at each end, and I would preload the bearings against each other. Okay? So I can preload them either by putting a step on the outside or a step on the inside. So for example, an easy way to preload bearings is to put a sleeve on the shaft. So right now here, I just put a sleeve on the shaft because I'm trying to use a standard off-the-shelf shaft, like a dowel pin, so I don't have to machine it. So I just slide the sleeve over it. And now what I want to do is push the two bearings by the housing to squeeze them together against the sleeve so they're preloaded. Now if the housing isn't accurate enough and you are worried about the preload, the usual way to solve it is by putting a spring washer or a wave washer. A wave washer is a washer which has a wavy shape which can be squeezed to be flat. So if I put a wave washer here and a bearing, the preload is not so critical because there is some flex in the washer. So I flatten out the washer, and now if I do that, there is no play in the shaft. Okay. Now if I wanted to put this into a housing made from spot welded sheet metal, the wall thickness is too thin to hold the bearing. So what you'd have to do, you'd have to, when you fabricate the box, you'll have to beef up the wall a bit. And if you look at this gearbox, you can see, first you can see the wave washer here preloading the bearing, but you can see there were some water jet cut additional plates which are permanently mounted with screws on the box, and these are thick enough to contain the bearing. Okay? Now, so the question is, how can you get them exactly aligned? Because of course you can't really rely on bending the sheet metal to align it. So the way it was done here, part of the alignment came from the fact that I'm using welded nuts which have self-aligning holes, and I'm using flathead screws which have a taper, so when I tighten the flathead screws they pull into position, this part, but it's only accurate for low precision stuff. If this was high precision stuff, I would have to line bore it. Line bore it meaning after it's all assembled, I would have to put it, without the motors of course, I would have to put it on a drill and drill through both pieces at once, or if it has to be more accurate, I will have to take a boring head with a long tool and bore through the first and go down bore through the second in one mounting. Okay? Now, so the inside shaft would have to have some space there. Now these would have to have some snap ring inside because it's hard to bore with a step where the step is on the inside. So the easiest way to do it here would be to cut a groove with the boring head, put in a snap ring in the groove, so the bearings will fit into these blocks and be stopped by the snap ring, and this tube will be long enough to preload. Okay. Here there's another possibility which is also okay. If it's not loaded heavily, you can use regular screws, flathead screws. You can pre-bore these plates and you can align them after assembly. And you can maybe epoxy them in place. The difference is that if you align it after assembly and it gets knocked can go out of alignment. If it's registered with a step and board, the step holds it in place. But here in this case, the easiest would actually be to prepare two pieces which have a board step, so the bearing cannot come out. And then you put them in, and then you align the second one to the first one after the whole thing is built. Now, one thing I should say about bearings is that, first of all, a very good supplier for bearings is vxbbearings.com, which have very good bearings, very cheap. But what's more interesting, there is one size of bearing which is an outstanding buy, and this is the 8 millimeter ID by 22 millimeter OD bearing. And this bearing costs about 25 cents, even at very, very high quality, like ABEC 5 comparable. And the reason they are there cheap, because they are used by all skateboards. So there is such huge supply that you can get those so cheap, and so try to use them for everything you can. The other bearings sell for about $1 a piece, which is also very cheap. Be very, very careful. As you know, the bearings are rated by the ABEC quality, ABEC 3, ABEC 5, ABEC 7. There is one company supplying this bearing that the company name is ABEC 7. So be very, very careful when you see in the ad ABEC 7 bearings, if it's not cheap bearings made by the ABEC 7 company that's sold by VXB. But even the general cheap bearings for 99% of the jobs are accurate enough. Now, one other point, if you end up with a fit which is a bit too loose, like the bearing is a bit too loose on the shaft, too loose means there's any play, or the bearing is too loose in the housing, then the Loctite provides a pretty good solution. You just put one drop of Loctite, let it run all around. It has a very high wetting power. So as soon as you add a drop of Loctite, it will run all around. You have to set it overnight, and it will take up the gap. If you ever have to push it out after it was Loctited, you have to heat it up with a heat gun to about 150 C, then it softens. Same as epoxy. Once you heat it up to 150 C, it's completely soft, you can push it out. Okay, so let's just talk for a few minutes about design philosophy. How do you approach designing a part? So the first rule of design is there is a hierarchy in ease of making things. The easiest thing and the cheapest thing is make things of wire. If you can't make it of wire, you start thinking about sheet metal. If you can't make it of sheet metal, you start thinking of solid. Okay? But if there is an easy way to make it of wire, both as one-off and production, it's the fastest. Good example is this wire bottle caps. You put it down, it latches beautifully, it opens beautifully. So, especially if you design for production, there is two reasons why design with wire is cheaper than anything else. The first reason is that if you make things from wire, there is zero waste. Making it from any other material has waste, right? Because the wire comes on a spool, there's absolutely zero waste. The second thing is there's minimal finishing, because you don't have to deburr the corners, you only have a sharp end to the wire, the rest is all smooth. If you bend it smartly, the sharp end is hidden, like in this case, where it's hidden here or hidden in the glass, there's no deburring. But there is another reason, especially these days, why if you design for production, you always think of wire first, because there are CNC machines which bend wire into any shape very cheaply. And in the old days, it was a machine with a mechanical setup, it was tooling, it was expensive. But the new type of machines, the wire is just fed out like this from a bushing, and there are 4 computer-controlled fingers which bend the wire as it's fed from the bushing. So as the wire or tube, could be tube 2, as it's fed out of the bushing, it's bent. And because you have 4 fingers, it can be bent in anywhere in a full circle. So this whole piece can be actually fed out from a CNC wire bender, and you see it take shape in the air by itself without any tooling. And that's an immense advantage, that there is no tooling to get any shape you want. Okay, so this is wire. Now, if you can't make it from wire, you start thinking of sheet metal, and we talked a lot about water jet and sheet metal, so we don't have to cover it, but there is some things which actually work very well with sheet metal and even better than solid. An example, one example is, this is something very common, say for a computer terminal holder, a monitor. You want something which is easily adjustable and easily lockable. Okay? So this thing, when you lock it, it's totally rigid, much more rigid than any machine form solid lock is. The reason of this is that it has many, many surfaces. So the total friction gets multiplied by the number of surfaces. It's basically the same idea as what's called a multi-disc clutch. There is some clutch in mechanical engineering called a multi-disc clutch, the same principle. So a very small hinge can be locked and have immense locking power. So you should always think, is there a way to make it of sheet metal instead of machining it? Because once it's sheet metal, of course, all the techniques we looked at before come in handy. Now, if it doesn't work, it has to be built from solid. You can make it from solid. But now, when you make it from solid, you start looking at the accuracy and at the precision of the parts. And you start thinking about it. First, what are you after? I already explained before the difference between strength and stiffness. Are you after stiffness or after strength? And if you need precision parts here, are they adjustable or not? If they are not adjustable and you really rely on brute force precision, there is really no shortcuts. Yes, you have to be like this, lapped or scraped, and everything has to be. But sometimes when you think of it, things are adjustable and you just want a precision feel. You want adjustability. You want a nice smooth feel, but the absolute position is actually adjustable. And in these cases, you can achieve a very nice precision feel just by having one side accurate. For example, if you have a set screw adjusting something, or a screw adjusting something, it feels quite rough. The reason why it feels rough, because the end of the screw has bears, it's not precise. The surface it's resting on immediately gets scratched by the screw and it's rough, and the whole thing feels rough. Okay, so when you try to adjust it to a micron, it's quite a rough adjustment. But if you just put a ball from a ball bearing between the screw and the surface, okay, it feels completely smooth. And the reason is that even if one surface is rough, it slides on a very smooth surface, it feels completely smooth. So you have to think, is there any place where I can insert precision parts into what I'm designing without having to machine it to precision? So if you have shafts and holes, you can use very precise pins, like dowel pins or roller bearing pins. So you don't have to make the shaft precise, you can buy it precise. If there is any kind of adjustment, the best idea is this ball in the adjustment to give it a nice feel. Some other ideas like that, but basically you have to remember, if you don't need the strength or the stiffness, if you just need the nice feel of precision, you don't have to do all this. Okay, you just need, say if this was rough and it's sliding on a perfect surface, it already feels smooth. So and if you can insert this perfect surface without having to make it, then you achieve what you want. Now, the second thing you have to think of the design is this a design for an instrument, which means there's really no load on it. It has to be very accurate, but there's no load on it. Or is this a design for a machine which has to have huge stiffness, has to carry heavy load, and maybe has to be wear resistant? So if it's a design for an instrument, you can use techniques like a kinematic mount, which is very convenient. It can be removed, replaced, self-adjusting. It's very convenient. If you have surfaces resting on each other, it can rest on very small points, so there's very little lapping, very little fixing. But if it's a machine which carries a big load, you can't use any of these concepts, because a kinematic mount by definition is a point contact. If you have a point contact, it cannot carry any load, because there will be infinite pressure at the point. So basically what will happen, it will indent. So if you have 3 balls and 3 V-grooves as kinematic mounts, you have basically 6 contact points, and if you put pressure, there will be infinite pressure at these contact points and deform the grooves. So there is a big difference between designing an instrument and designing a machine, like a machine tool, because machine tool pretty well relies on over-constrained design or full surface bearing, like this was, while an instrument can get away with kinematic mounts, point contacts, and so on. So this is another dimension to the design that you have to think about it. Now, other things you have to think about it is if it's the design of a product, not the design of an experiment. If it's something which will be repeated, there's a lot of things you have to think of the design in terms of lifetime cost. For example, the thing will have to be maintained. So parts have to be easily removable, access has to be proper, and so on. And we wouldn't get into that here in this course. But one thing I found out, people always underestimate if there is any kind of electrical cabling needed. So I say if you design some servo system and you lay out bearings and covers and everything, most people don't think through where all the cables will go. And then when it's built, it's a mess because you didn't leave enough room to route the cables. So anything electrical, when you finish the design, you have to lay out exactly where every wire should go, every plug, every strain relief, and build it into the design. If you have in one system hydraulics and electrical, which is very common, like in CNC machines and so on, make sure you always put all the water or hydraulic tubing below the electrical wiring for obvious reasons, because electricity never drips and leaks. So when you open the cabinet, all the electrical relays and everything have to be on top, all the water hydraulics have to be on the bottom. If it's air, it could be on top as well, then you're not too worried. So there is a lot of considerations when you think of something for long life and production. It's a bit easier if you just make a one-off or a test for yourself. So that's basically the general approach to design. There's also an aesthetic aspect, because especially in a product, but even for your own gratification, it has to look nice. So there is a very interesting rule that if something is 100% functional, it's always beautiful. So for example, there is no such thing as an ugly nail or an ugly hammer, but there's lots of ugly cars, okay? Because in a car, not everything is functional. You have all kinds of spoilers and additions which are not functional, so sometimes it's very beautiful. If the person who designed it had very good taste, sometimes it's ugly. But if you look at something 100% functional, it's always beautiful. Like airplanes are all beautiful because there is no room there for additional weight. Okay? Also, if you design a part where there is no extra metal, in other words, when it's thinned out where the low stress areas are, it's always beautiful. Think, for example, of a bow and arrow, of a bow. So a classical bow is thinner at the ends because there's less stress there. But if you made a bow which gets wider at the end, it will look ugly. Because intuitively you would feel it's not 100% functional. There's extra material that you don't need. So it's a good rule to keep in mind is if you want it to look beautiful, just design it to be 100% functional. Remove all the material which is not needed, it will become beautiful by itself. That's it.